Hello? Okay.
Okay, so for the last sort of regular talk, we have Gautam, who's going to tell us about infrared finite scattering in QFT and quantum gravity. Take it away.
Okay, well, thank you. Well, thanks to the organizers. This workshop is, as you know, someone who doesn't actively work directly on celestial holography, this is really illuminating. And also thanks to the organizers for being so accommodating and letting me regain my voice before I. So let me know if you can't hear me or things are unclear. I can try to shout if necessary. So I was asked to give I think the title or the denomination was a technical research talk on this kind of fairly long and technical paper with Bob Wald and Kartik Prabhu. The punchlines of this paper are actually fairly simple in my opinion and non-technical. So my goal in this talk is to give you those punchlines and allude to why we had to build the machinery we did build in this paper to prove the statements that we ultimately got to. Okay, so right, so what we want to do is to consider what infrared finite scattering theory, in quantum field theory and quantum gravity. So does there exist a well-defined S matrix on this theory, in quantum field theories and quantum gravity more generally? And so there's some follow-up work to appear that I might allude to at the end of this talk. Okay, so we haven't had lunch yet. It's early still, so let's just go slow, and let's do a lot of review. Mostly this will also set notation and kind of orient us to what is necessary to address this question. So the first thing, of course, is the memory effect. And as you all know, and you really, this really should be review, if you have a system of test masses in the gravitational case, and I allow a burst of gravitational radiation to pass by the screen, these test masses will relatively oscillate, as we all know. But if there's a non-trivial memory effect, these test masses will become permanently displaced due to the passage of this burst of radiation. And you can compute this displacement. It's given by this memory tensor, which maps the initial displacements of the test masses to their permanent change of the final displacements at leading order in the distance from the source of the radiation. Okay. And as you all know, I'll be saying that a lot, I guess, in the first. So there's also an electromagnetic memory effect. I don't need a whole array of test masses. I just need a single charged particle. I can allow a burst of radiation to hit my charged particle. And at leading order in the distance from the source of the radiation, if my charged particle gets a net momentum kick, that is the electromagnetic memory effect. Okay. So what kinds of bursts of radiation am I really considering? Well, I'm really considering kind of scattering radiation, like radiation arising from some scattering event. So this could be, the scattering of some charged particles in QED or in electromagnetism, or the merger of some black holes or stars in gravity. And the key feature is that at asymptotically, early times and late times, the radiation is fairly negligible, but can become fairly significant at intermediate times. And if I, had some detector located near scry, what would I look at in terms of the waveform? Well, if the radiation has memory, that's that momentum kick I told you about before, that by Lorentz force is the integral of the electric field. That means that the memory is this integral of the electric field along scry. And in terms of the vector potential, corresponds to a permanent change in the vector potential between early and late times. Okay, so it's this permanent offset, as you all are very familiar with, in the vector potential that gives rise to the signal that you have memory. And of course, in the gravitational case, there's an almost, these pictures should look basically identical to you. And the memory can be now expressed in terms of the integral of the news tensor, the gravitational radiation degrees of freedom. And if I write in terms of the metric, that corresponds to a permanent change in the metric between early and late retarded times. Okay, so that's the relation, that's how you see memory in terms of the waveform. As you all are aware, it's very useful to rewrite this expression, or in terms of kind of charges and fluxes at scry. And that's going to be kind of essential to understanding the question I posed on the first slide. And so let's just do this. Again, we're just reviewing here, but I want to set my notation and draw some nice pictures. So, right, so I can consider these large gauge charges, which is, again, as you know, the integral of the radial component of the electric field over some cut of here future null infinity. If lambda was a constant, this is of course the total electric charge on this cut, but now we're letting lambda be an arbitrary function of angles. And the reason one would want to consider this is because I can rewrite this outgoing radiation, this outgoing memory, in terms of the difference of these charges, one at future time-like infinity, as well as the charge at spatial infinity. And then there's also a contribution due to any massless charge current flux that goes out to null infinity. Okay, so this right-hand side computes for you this memory effect in terms of these charges and this flux of massless charge current. And of course, one can also, I did this for the out data, you can also do this for the in data, where you want to, well then, if you write this, or you compute this charge at past time-like infinity, as well as the charge at spatial infinity, the difference of these charges, as well as if you had any incoming massless charge currents, would give you the incoming memory. And as was nicely pointed out by Andy, and then there was a lot of work to really show this in the electromagnetic, and then on the next slide, the gravitational case, these charges actually match at spatial infinity. So the matching is that, so if I take these cuts all the way to spatial infinity from the far past, or take this cuts from all the way to spatial infinity from future null infinity, these charges, the limiting values of the charges from the past and the future, antipodally match in the sense that, well, in the sense that I'm describing here. Okay, so that's the electromagnetic case, of course, and this is just still mirroring. You also have a same, almost exactly same situation in the gravitational case. These charges now are defined in terms of the integral of this particular Weyl component. Yeah, go ahead. Right now, it's a purely classical discussion, but there'll be I'll say when I go to the quantum theory. No, I won't consider the charges on any finite cut, on any particular cut. I'll only be considering their limiting values at time-like infinity and spatial infinity. Yeah, so you can try to look at charges defined on a finite cut. You run into significant problems at any finite cut, but the limiting values are all that you need to talk about the infrared behavior, which is what we're going to need to talk about. Okay, thanks for the question. All right, so, but again, yeah, so this is all in the classical theory right now, but then we'll turn to the quantum theory, where I'll use some of these features. So you have these charges, you can, have this outgoing memory, which can be expressed in terms of the difference of these charges, one at time-like infinity and one at spatial infinity, as well as now you get a contribution due to the total gravitational radiation energy that makes it out to null infinity. That's this integral of the nu squared here. And well, the situation is exactly identical in the past in terms of the in memory, in terms of the difference of in charges at time-like infinity and spatial infinity, as well as any incoming gravitational radiation energy. And again, these charges match in exactly the way I mentioned before. Okay. Okay, so now let's turn to the quantum theory. And so let's first do the kind of standard Fock quantization, and in particular, we'll focus on the radiative degrees of freedom. So the first question you could ask is, well, what do you mean by quantum gravity or quantization of gravity? But the key point is, and I guess this was first pointed out by Ashtekar in the 80s, I mean, the radiative degrees of freedom, the kind of kinematic degrees of freedom of quantum gravity can be quantized even in the absence of any, specifying any particular bulk theory. So, and everything I'll be asking about in this talk can be boiled down to kinematic constraints. And as a result, I'll be really just using this asymptotic quantization at scri plus and at scri minus. Okay, and if you continue on with this, this idea, you can write down the kind of standard Fock space. So in this slide, I'll just focus on gravity, but you could do the same thing for the electromagnetic field. The standard Fock space is constructed from a one particle Hilbert space of gravitons with this particular norm. So this norm, it's not so important that you memorize this norm. All you need to know is that it depends on the Fourier transform of the metric at scri. There's this factor of omega here. It's an integral over positive frequencies, and it's an integral over the two sphere. Okay? But even at this stage, we can see that there will be a problem, which is the key issue that we'll be addressing in this talk, which is that if I plug in a solution with memory into this norm, well, if the memory is non-zero, that means that the change in the metric between early and late times is non-zero. If I Fourier transform that, that's at low frequencies is the Fourier transform of a step function at very low frequencies, and therefore must diverge like 1 over omega. And consequently, if I compute the norm of this out state that I've decided to consider, it's logarithmically divergent at low frequency. Okay, so what does this mean? Well, the standard Fock space of gravitons in this particular case, but photons in the electromagnetic case, does not contain any states with memory. Okay? And any state with memory will have infinite norm in the usual Fock space. There's absolutely nothing physically wrong, and I don't have to convince this crowd, I think, with states with memory. They unavoidably will occur in scattering. However, infrared divergences will arise when you try to pretend that they are supposed to belong in the standard Fock space. Okay? So when we say that we want the words infrared finite scattering, we need to amend this prescription that the outstate lies in the standard Fock space. Okay? So what do states with memory look like? I gave you a bunch of states with no memory. So what do states with memory look like? Well, it's really trivial to write down states with memory. If you give me a bunch of states with no memory, it's very easy to start writing down states with memory. How do you do this? Well, states with memory, as I said before, are perfectly legitimate states, and a Hilbert space of states with a particular value of memory can be easily constructed starting with the states with no memory. So what do? You just perform this. I mean, I use the word field redefinite. I mean, it's just a trivial change of, you just take the operator on the standard Fock space and you add to it a classical solution with your pre-chosen value of memory. So this is a trivial change in the level of the operators. Like this basically, this is I guess the technical term is an automorphism. It doesn't change the operator algebra at all, of course. And now you can do this to the correlation functions of the standard Fock space. And these correlation functions of this shifted operator are again perfectly well defined. There's absolutely nothing wrong with the correlation functions of this new shifted operator, of the shifted states. But the corresponding Fock representation, if you ask what is the representation under which these new shifted states live in, they live in a new representation, F delta, which is just unitarily inequivalent for different delta. So it's unitarily inequivalent to the standard Fock space. So in particular, just to put a finer point on it, if I act delta on any states in this new Fock space, F delta, they're all eigenstates with eigenvalue delta. Okay? And if I could have done this shift for a different delta, and I would have gotten a different Fock space. And that different Fock space for a new value of delta will be inequivalent to this one that I chose for this delta. Okay? Go ahead. Yes, they're unitarily inequivalent as representations of the algebra. Yeah. So what is going on here? Or what have I just made? I've made the problem worse. But there are now an uncountably infinite number of in and out Fock spaces labeled by these deltas labeled by all the possible in and out memories that I could have. Okay? And the memory is not a conserved quantity. Okay? If I stand in a state with zero memory, I will scatter out to states with memory. Okay? And so the standard S matrix, this is a reformulation of the same statement that I guess people have been grappling with for quite a bit of time, but now recast in this language. The standard S matrix does not exist largely because you will scatter out, or you could potentially scatter out to any number of these F deltas. And I'll make a more concrete statement in the next slide of what kinds of things can you scatter out to. So if one wants to really go beyond inclusive cross-sections and have an infrared finite S matrix, you need to include states with memory, and somehow you need to put all of these uncountably, or a sufficiently large number of these F deltas together to have a well-defined scattering theory. Okay, so what are the choices? What can we do? No, I didn't say finite, a sufficiently large number, which is being addressed on this slide. It undoubtedly would have to, yes, you're right, yeah. So large is this, it depends on what space of memories, right, or something, so I'm being vague. Okay, so what sort of Hilbert space should we choose? Well, we need a sufficiently large number of these F deltas, or sufficient many of them, to ensure that the corresponding Hilbert space will scatter. Yes, Andy? Yeah, so the vacuum degeneracy, I think, is an interesting thing, but I don't think so each of these Fock spaces, you could have added an extra label, basically saying, like, even in the zero memory Fock space, not in my construction, you can basically, because I'm quantizing with respect to the news algebra, if you quantize with respect to the shear, you would have an additional degeneracy. But that doesn't come into the infrared. Yeah. Well, I think it depends on the representation of what algebra you choose first. So I'm just sidestepping the vacuum degeneracy because it doesn't play a role in these infrared, in the fact that the outstate has memory. But it is an interesting point. I mean, yeah. Okay. Yeah. Okay, so then I think they are mathematically equivalent, probably statements. But yeah. It's mathematically equivalent. I would say it's mathematically equivalent. It's just that we didn't, though, if the statement is that you need to include the outgoing radiation that has memory, we're saying the same thing. It's just that in the statement that whether or not the vacuum, like, you can interpret the memory as the fact that you have an outgoing radiation with an integral of news, not zero. You can interpret the memory also as the fact that the shear between early and late times is changed by a super translation. Yeah. No, I would not get any different answer. Okay. Where was I? Probably on this problem. Okay, so what is the problem? Well, as I said before, the memory is not conserved. So if I just start taking these F deltas together and putting them together in any arbitrary way, there is no way to ensure that construction, if I just stitch these F deltas together, that will be preserved under scattering, right? There's no, if that's not built from any conservation law at all, there's no real reason to assume that such a way of putting these F deltas together would be conserved. We still tried. Maybe I'll just finish this line and then. So we still considered several possible options. For example, you can consider the direct sum. One really bad technical property of this direct sum is that it's an uncountably infinite sum here, which means that this space is non-separable. You can't choose, like, first of all, even if I stuck with a state of definite memory, it's not even clear it would scatter into itself. But even if it did, like, well, not even if it did, but the fact that it's an uncountable sum means that, if you want to compute amplitudes and sum up a bunch of amplitudes to compute your out state, you can't do this in an uncountably infinite Hilbert space. So this is a very bad construction. One could refine this construction into what's called a direct integral, which is basically you now look at smooth distributions over memory. The devil is in the choice of this measure, which is a measure on the infinite dimensional space of memories. We looked at all possible Gaussian measures and showed that none of those work. I'm not going to explain that in this particular talk. That's a whole nother, I guess, technical research talk that I could give. But I can talk about it afterwards if anyone is interested. But neither of these work, and maybe you shouldn't even consider them in the first place because you're not building them off of any symmetry principle. Okay? And so the real question is the highlighted question: does there exist an in-Hilbert space of states which scatters out to a pre-chosen out Hilbert space? Pre-chosen being the operative word, right? That's how we do scattering theory usually. Okay, and you had a question. No. They can have arbitrarily close energy, but the energy operator on these F deltas is bounded below by 0, but never reaches 0. Yeah. I can't hear you. No. So that's a very well-known theorem in measure theory, is that there is no Lebesgue measure on the space of infinite dimensional space. You could try Gaussian measures. Those are not translation invariant. No, it's a physics statement that there's no. Oh, sorry, go ahead. Yeah, that's the key problem. You want your states to have finite norm, but if you integrate over if you just integrate over a Lebesgue measure, you're not. I mean, over an infinite dimensional space, you'll get the space of states that satisfy that norm condition will be nothing. Like, yeah, but the path integral uses a Gaussian measure. That's the key point of the path integral, is that the kinetic term gives you a Gaussian measure that controls the integral. So that's all I'm saying here. You pick a Gaussian measure. But we looked at that and we showed that that doesn't work.
Sorry, maybe I'm just.
Sorry, say again? I didn't hear the first part of the sentence. This last question? No, I'm posing it at this point. I'm not saying it's known. No. Well, I mean, in massive QED, there is a prescription that I will get to in the next slide. But I will explain why that doesn't work. What? The measure statement is the well-known or not the well-known, but is the known statement that I was making.
Sorry.
Yeah.
Did you find there's no measure?
We proved that there's no Gaussian measure that is a representation of it is a representation of the out algebra, including the BMS group. There is no Gaussian measure. That's what we proved. It's possible, yes. Basically, at this stage of the talk, I'm just guessing, right? I'm just writing down possible choices. I'm answering the question, what sort of Hilbert space should we choose? Let's just try a bunch of them and see if there's any, nice Hilbert space that includes a large number of these F deltas that could be a representation. And I'm saying, at this level alone, it's also already really hard. If you Well, and it's going to get harder, is all I'm saying. And we'll get to that in the next slide. Okay? Any other questions? They don't belong in the standard Hilbert, the zero memory Hilbert space. That's right. Yeah. That's right. That's what I did. So this new F delta has a norm in which states with memory are finite. If you construct a new norm, you get a new Hilbert space. A Hilbert space is defined by a norm or an inner product. And I'm saying the Hilbert spaces that you get when you go to a new norm give you an inequivalent Hilbert space to the original zero memory. Yeah, and yeah, I should say Ashtakarta is not the first person to have written down that norm. But for states with zero memory, that if you just like do the electromagnetic case, like the standard Fock quantization in the bulk, you just pull it back to scry. That's the norm you get. That's the norm you get. You know, reduce an index everywhere. Okay, I think I'm done this slide. Okay, so as with any long-standing problem, two Russians have already solved it, and in this particular case, Faddeev and Kulish in the 70s really, from my perspective, miraculously solved it. And this interpretation that I'll be addressing is, well, Faddeev and Kulish did not give this interpretation. This interpretation was given later by a number of authors. Actually, I think one of the clearer ones is Andy's paper that he mentioned with Malcolm Perry, Anna Maria, and Dan. But this is let me just give you the key idea. The key idea is that the charge at spatial infinity is a conserved quantity. So let's start there. So if I start with an in-Hilbert space of eigenstates of some of this conserved charge with some fixed eigenvalue, that will map to an out-Hilbert space with the antipodally reflected eigenvalue. And I now finally have some control over this problem. Okay, this is not how could it, yeah, go ahead. Yeah. Right. I completely agree. Yes, that's right. Yeah. Yes. Yes. Exactly. That's right. Yeah. Yes. So. Yeah. Yeah. That's right. That's exactly right. But there's a key reason why it chose this, which is that you get a full Hilbert space of states that scatters into itself. If you look at just for an arbitrary in-state, what is the space of out-states that you could get that conserve charge? It's still an uncountably infinite space. You could write down amplitudes between particular points in that outspace between the in-state. Yeah. No, I completely agree. So so I guess stick around to the last slide, and I'll give you a way of doing the scattering theory that use this construction. But we have to first see exactly how bad is this construction, besides your complaints. It gets worse. So, yeah. That's different. Not radiation. This is, yeah. 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 What, so, yeah. Yeah, exactly. Yeah. Well, because you're including this coherent clause. Well, yeah, so you can view this slide as how badly do we have to mangle scattering theory to get a infrared finite S matrix, which I guess is in line with Andy's comments. Okay, so we're not done. So so what are these charge eigenstates? Well, Andy kind of alluded to them already. They're states in which the in electromagnetic memory is highly correlated with the incoming electron. Okay, and these are what I guess has in the literature has been called these dress states. So let me just give you a picture. So I could send in, so the first step is don't send in a wave packet of some electron. For the first step is send in this plane wave state. Okay, I'm going to correlate at the level of these plane wave states alone. So they're highly correlated. So you said I'm fixing the charge at spatial infinity. I send in some plane wave state that has a definite charge at past time-like infinity. And if I fix the charge at spatial infinity, I can exactly solve for the incoming memory that I need to send in this coherent cloud of radiation that I have to send in. This electromagnetic memory state can have any hard radiation you want to add to it, but the zero frequency mode is exactly fixed by the momenta of the incoming particle. Okay? And that's what you do here. And then you can construct a wave packet, of course, of these dressed electron states. And this gives you a one particle Hilbert space of these dressed states. The corresponding, so these are the dress states that people are talking about. And if you're sending in one particle, you can then do n particles and get a whole Hilbert space of states that are all dressed in this particular way. But what was not appreciated at the time of Faddeev and Kulish, but was appreciated afterwards, and is pretty clear from this new reformulation of everything, is that these charges are not Lorentz invariant. But this is a whole Hilbert space of eigenstates of this particular charge. So the Lorentz boost cannot act on this Hilbert space. Even an infinitesimal action will break this condition unless you set all of the charges equal to 0. Okay, and this was appreciated, I guess, 9 years later by these authors here, that you really need to set all of these charges equal to 0 to have an action of Lorentz. So or another way of saying this is that the angular momentum for all of these states is undefined unless you set all of these charges equal to 0. So this includes the total electric charge. So in order for this to work, so what did I say before? I send in an electron. I really cheated. You also have to send in a positron, and scatter and send that in as well and dress it in the exact way that I was telling you before. And if you do that for both of them, then you can now stick to this zero charge sector. And this paper here kind of strangely said, well, if I'm scattering some electrons over here, who's to say there isn't a bunch of positrons behind the moon somewhere, and the total charge is actually 0? So why can't everything just be dressed, and I hide all of my extra charges somewhere really far away or in my back pocket or something? Okay. So the, I didn't, well, This is an old, I did not mean to put the citation for that there. I'm sorry. But okay, anyway, the key point is, so if you take all of these huge grains of salt, then this Hilbert space constitutes a space of states with finite energy and angular momentum. It contains all hard scattering processes, you could argue, because you could tune all the soft coherent radiation to very, very low frequency, and you can hide all these extra charges behind the moon, and is separable. It admits a countable basis, so you can start computing amplitudes. Okay? So there's a well-defined unitary IR finite S matrix in massive QED. And in the next two slides, we'll see this construction absolutely fails in every other theory. Okay, what happens in massless QED? Well, you can just do the analog of the same construction in massless QED. You're pairing eigenstates of now the charge current flux, these incoming eigenstates of the charge current flux, with an eigenvalue that's a delta function on the sphere with this incoming memory. However, these required dressings have collinear divergences arising from these delta functions. So these collinear divergences are not new. People have known them for a long time. Kinoshita, Lee, and Naumburg, nicely show that there exists a lot of states with finite energy where you smear out these collinear divergences over some small angular window, and you can get well-defined out states with finite energy. However, all of the Faddeev-Kulish states necessarily have infinite energy. If you smear them out a little bit, you break the eigenstate condition, and you cannot have, they won't be eigenstates of the charge. So Faddeev-Kulish would say you have to keep these collinear singularities, and therefore the electromagnetic field has infinite energy in the outstate. Okay, what's going on in gravity? Go ahead. This addressing, well, I mean, the way the question is, what is the eigenstate of the charge? That's a basis independent statement. Oh, but then you have to sum them up in some way that you get an outstate with finite energy, right? Oh, well then, boost eigenstate. Oh, boost energy. And are they eigenstates of this charge? And they correspond to proper states? Well, so this proof of the eigenstates of the charge, I mean, is a basis independent statement. So it should be true in any basis. So I'm not sure. We'd have to talk to see how the. So I'm talking about energy in terms of the translation is correct. Yeah, yeah. Sure. I see. I see. So yeah, I mean, so I would say this particular statement I'm making is a basis independent statement, because it's just a statement of what are the outstates of the proper states with definite charge. But it would be interesting to look at what these boost states. It's the no, in this case, it's the large gauge charge. This is the super translation charge. Yeah, but I'm not looking at eigenstates of all the BMS charges or all the charges. I'm not including it. I'm not looking at eigenstates. Yes. Yeah. So maybe they're mutually compatible statements. Yes. Okay. Cool. I'm not trying. I'm not trying to be in an eigenstate of Lorentz. Okay. I'm only trying to. I mean, the Faddeev-Kulish construction is to use the charge matching of the large gauge charges alone to get an IR finite scattering theory. Yeah. Okay, so then I'm not trying to do that. Yeah. Yeah, so the statement here is that if you look at you just have an algebra of observables and you're asking what are the states that are eigenstates of the charge. I can, through that construction, I can choose a basis, but then you can check whether it's a basis independent construction in the sense that if I choose another basis, is it still an eigenstate of this charge? That's all I'm saying. Yeah. Well, it sounds like it's a diagonalizing Lorentz. It sounds like we're diagonalizing different operators. Yeah. Okay. So what's going on in gravity? I don't know how much time I have. Do you have like, okay, cool. So what's the case? Let's just do linearized quantum gravity. In the next slide, we'll do full quantum gravity. But in linearized quantum gravity, one can repeat this Faddeev-Kulish construction that's done by, well, Akuri and Tangmin, who's in the audience. And there, as was nicely pointed out in that paper and has been nicely pointed out before, there are no collinear divergences. I mean, you can kind of see that just from the fact that the eigenstates of now this, you're trying to pair eigenstates of this outgoing flux of stress energy. I'm considering a mass, I'm considering a case where we're doing linearized quantum gravity with massless sources, and you want to pair eigenstates of this operator with, correlated with incoming memory to get an eigenstate of this charge. And there are no collinear divergences largely because while this eigenvalue is a delta function, you get two derivatives here, and that smooths out the memory just enough that you don't have any divergences. Okay? Yeah. Are you saying there's no memory in massless QED? Yeah. Um, yeah, so I mean, so massless QED for us was a toy model. Like we were really interested in gravity. There are statements like by Wilczek and others that make the point that you're making, which is that the coupling runs and therefore you maybe shouldn't treat this theory too seriously, is I think the point that you're making. Well, the fact that the coupling running doesn't change the algebra of the out field. Like that doesn't, I'm not sure I see the difference. Yeah, yeah. No, I mean, I think, I guess the clarification I was going to make is distinct from your point. So maybe I just won't make it. So anyway, okay, so now if we consider linearized quantum gravity, we can do the same construction. It's less singular, as I mentioned before. However, we can't set the charge to zero. This would set the total, form momentum to zero, which, doesn't really, there's not a lot of states with zero form momentum. Another way of saying it, you can't really hide mass behind the moon. There's also the moon. So all of the Faddeev-Kulish states from this construction have undefined angular momentum. Or another way of saying is that you can't act with the boosts on this on any space constructed in this way. Okay, so what's the theorem or statements in quantum gravity? So let's just do vacuum quantum gravity because gravity self-couples at Scry, and it's already an interesting theory just to scatter in vacuum quantum gravity. Well, we can't set the total charge to zero. That would set the total form momentum to vanish. We're already going to have to break Lorentz just from the out point. But, I've been talking for about 35 minutes or so. And, I haven't given you a single infrared finite scattering theory. So why don't we just break Lorentz and see what happens? So we proved the following theorem, which is that the only eigenstate of the charge at spatial infinity is the vacuum state, which I'm defining as a state with 0 energy and 0 memory with vanishing eigenvalue. Okay? And let me just give you a little bit of intuition behind that. Well, in this particular case, I mean, so this is not exactly how we prove this statement, but it's analogous to how we are showing it. So if the memory and the energy flux are not independent quantities in gravity. These are both constructed from the radiative data. And in gravity, so you could imagine sending in first, try to do the addressing. Send in a state with just energy, no memory. Okay? And then what you want to do is you want to, in the spirit of Faddeev-Kulish, send in a little bit of radiation with memory to exactly cancel the amount of energy that you added. But that little bit of radiation, in order to have the final state be a normalizable mode, has to carry a little bit of energy. I mean, it can be as small as you like. But that adds to this term a little bit. And then you can send in a little, you have to send in a little bit more memory. And that, that memory, that radiation with memory has a little bit of energy, as small as you like. And that adds a little bit to this term. And what we show is that that sequence of events, of someone writing down these steps on a piece of paper never converges unless you started with just the vacuum state. Okay, so what is the punchline? There is no preferred Hilbert space for scattering in quantum gravity. Non-Faddeev-Kulish representations, these integrals over memory spaces, also don't work. I can talk about why, but all I've shown you really right now is that the Faddeev-Kulish construction absolutely fails. Okay, so what do we do? So how do you do scattering theory if you don't have a preferred Hilbert space? So I hope I impressed upon you, and this is quite literally my last slide, so I hope I'm not running too over. The space of correlation functions, which are very easy to write down, this is largely what we did in the paper, of all states in scattering theory, for the in and out states of finite energy and angular momentum and everything, are perfectly, and with or without memory, are perfectly well defined. The statement we're making in the paper is that they just don't all fit into a single separable Hilbert space that scatters into itself. Okay? So how do we think about this? Well, let me just say a kind of trivial but important statement. Any state in a Hilbert space can always be written down as a list of correlation functions. But the converse statement is also true. If you give me a list of correlation functions satisfying commutation relations and positivity and whatever, one can construct by a very simple procedure known as the GNS construction, a Hilbert space where this list of correlation functions sits in as a vector in the Hilbert space. It's all packaged up into one vector. So viewing a space of states as a list, or a state as a list of correlation functions, or a vector in the Hilbert space are essentially equivalent. So there's a really nice review article. This is known as, the scary term of algebraic quantum field theory. But this is all algebraic quantum field theory is saying. If you work with correlation functions and you don't have a preferred Hilbert space, nothing is wrong. If you try to fit all of your states into one Hilbert space, you can run into issues which are infrared divergences. Okay? And there's a really nice, more recent review article by Ed Witten on this, I think last December, it was published. Okay, so by considering states as lists of correlation functions, one is now completely free from choosing in advance any particular in or out Hilbert space representation. And starting with some in set of correlation functions, with whatever memory, whatever charges, you can dress them, Andy, if you want to. You can decide not to dress them. You can send in bare electrons with just their Coulomb field. One should then be able to calculate out correlation functions by the same sort of LSZ perturbative methods used in S-matrix calculation. And since I'm running a bit over time, I won't go into the details of exactly how we propose to do this besides saying these statements. But I think it would be really interesting to further develop such a manifestly IR finite scattering theory. Okay, let me end there. Sure. Should we all count together in the room? Yeah. Yeah. The difference is that if if you're computing an amplitude, you've pre-chosen what the out Hilbert space looks like. And so therefore, what I'm saying is, if you never do that, if you just you define your scattering theory as a map between a list of in correlators to your out correlators, the out correlators with memory were nowhere near, weren't as there were no IR divergences when I wrote down correlators with memory with correlators without memory. The only problem is that if you try to presuppose that the correlators without memory with memory live in a zero memory representation, you get infrared divergences. So the statement is that the key step is to never assume this. And I think that's really, I mean, what I'm trying to show is that I think that is really the way to proceed. So a correlator is like, you have an out algebra and you have an in algebra. A correlator is a list of correlation functions on the, let's say the out state. If you give me an out state, that's equivalent to a list of correlation functions of the out algebra. And the question is, or the way to proceed, in my opinion, is that if you give me a list of in correlation functions on the in algebra, by kind of following the same kind of LSZ perturbative methods, but not assuming pre-choosing what the out Hilbert space looks like, you map the in correlators to the out correlators. In and out meaning correlators on the respective algebras. Okay, I have ideas on how to do this, but I didn't include it in this. Yeah, go ahead. Well, there was a series of steps of mangling of the theory, right, to get to the fluke. And I'm just, well, I tried to explain. So it's basically the statement that there exist. So the key idea is to find a full Hilbert space of states of eigenstates of this charge. The question that needs to be addressed is whether or not there exists a space of physically reasonable states that are eigenstates of the charge. In massive QED, it just so happens that you can write down a full Hilbert space of states that are eigenstates of this charge. In gravity and all other cases, that's not possible. And for them to have well-defined actions of angular momentum and energy and, well, in full quantum gravity, it's just not possible at all. No, I mean, sure, yeah. Yeah, okay, but I think, yeah, okay. Yeah, so the model abelianizes, but the model of the algebra, for example, is free at Scry. Like there isn't any, I mean, the data that you need to specify is free data at Scry. Yeah. Yeah, so what goes wrong in that construction is that when you add the coherent states of gravitons and you include the contribution due to the news, so this is now coming in at higher orders, you will break the eigenstate property. Well, okay, let me say two questions. You would see the violation of Lorentz at all orders in perturbation theory. I think at second order in perturbation theory, you should see this can start to contribute. And that should destroy the eigenstate property. Yeah. Yeah. Yeah, so that goes to the vacuum degeneracy question. Well, my algebra is the electric field algebra, and so therefore I don't have to take this vacuum degeneracy into account. You can also, and you can amend, I mean, it still is the same thing at the end of the day, but the way you arrive at it is just different. That's all. Yeah. Yeah. There's no difference in the argument. It's just the question of, yeah, I think it just depends on what algebra you start with. Well, except for the action of Lorentz. Yeah. Yeah. So, yeah, if you're okay with a breakdown of Lorentz, then yeah, linearized gravity would work in that sense. But yeah, I mean, you can't ask, for example, is the S matrix like Lorentz invariant? Because there is no way of asking this question in this context. So.
Other questions? Going once? Going twice? Okay, let's thank Gautam again. Okay, and we'll wrap up with some discussion from Andy.